thing we wrote down, last thing we talked about.
Absolute zero.
Absolute zero, right. So the Kelvin scale, good. So what I need you to write down in your notes, and you're going to take some notes on the video I'm going to show you here. So let me close these things out. Okay, this video here is on kinetic molecular theory. Kinetic molecular theory. There's 4 parts to this, three really. 3 and 4 kind of lumped in one. So the video is going to tell you what the theory means. I'll pause it. You're going to write that down. Then it says something about kinetic energy. I'll pause it. You can write that down. And it doesn't talk about this, but I wish it did. For those of you at home. What is it? Rubber band. Okay. So if this was a new rubber band, it's pretty new. I stretch it, and I go. It basically goes back to the way it was before I stretched it. Would you agree? Basically? If they get older, they stretch out. It's not the same, but would you agree?
Me?
Yeah.
Yeah.
Okay, good. Okay. Sometimes, we have issues. So, yeah, just think about this. Okay.
Oh, nice.
All right, lights please. I guess Caroline or Adriana? Caroline's got it. So, watch this, then we'll take some notes. Go ahead, all of them, why not? Let's make it nice and dark, easier to see. All right, so yeah, watch this. I'll pause it when I want you to write down some stuff here. But this is kinetic molecular theory, and that's what we're basically learning today. Oh, one more thing. Ideal gas. Make sure on the worksheet due tomorrow, which is the back of that other sheet, you define what ideal gas is. So we're going to be talking about gases here with this kinetic molecular theory. So it's appropriate to define ideal gas. What is an ideal gas? So we'll talk more about that tomorrow. All right, that's it. Now we're ready to go.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving.
Okay, what's the kinetic molecular theory?
Something about atoms moving.
She talks too fast.
Theory that.
Oops. Okay.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving.
You can paraphrase it. So what is it?
The theory that
All matter is made up of atoms, molecules that are
moving.
always moving, right? So please write that down. Kinetic molecular theory says that matter is made up of, we could just say particles. Atoms and molecules are particles, whatever you want to write, that are constantly moving. So everything is always moving, except at absolute zero. The theory, remember, at absolute zero, I don't know if you wrote it down, it's okay if you didn't, but the theory at absolute zero is all motion stops. So we're saying everything above absolute zero, this theory is basically true, because what are solids doing? Vibrating, right. And everybody else, liquids are moving a little bit quicker, gases are moving a lot faster. So what you're seeing here, these little squeaking water molecules, are vapor, right? They're gas at this point in the video here, because they're moving all over the place. Okay. So that's the first thing we wrote down, basically the definition of that.
These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles...
How do they move around?
I wasn't even paying attention.
Randomly, thank you, Trevor. Let's write that down. Particles move randomly. That's another thing about this theory. So we had the definition. That's not really part of it. There's 3 or 4 things that we're going to list. That definition is not one of them. So one of them is, though, that the particles move randomly. So that's like number 1. Particles move randomly. And I don't know if they say this, but I told you this last week. They move randomly, but how? Straight lines, right. Randomly, and they move in straight lines too. Okay.
Have high energy, and in low temperatures, the particles have less energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy.
Okay, we're writing that down. High temperatures, they have more energy, more kinetic energy. Low temperature, they have less kinetic energy. Popcorn will never pop. You put it on the counter and just have it sit there.
It's like really, really hot.
Unless it gets really hot in the room, right?
Yeah.
So the point is, assuming the air temperature in your house is pretty stable, and it doesn't get hot enough to pop popcorn on the counter, if it does, you're probably going to die. So I'm sorry about that. So that would be too hot to live in. But the point is, it's a pretty good analogy that if it heats up, particles inside it start moving very quickly, lots of pressure build, and then it pops. But if it's just sitting on this table here, it's going to be too cold. Particles aren't moving fast enough to pop that. Not enough pressure is going to be built up. That's the next thing we're getting out of this. Fast-moving particles, a lot of kinetic energy because they're hot, most likely. Slow-moving particles, like right here, they're cold. They lost all their energy, so they're moving slower.
The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water...
Did you see the one drooling?
Mm-hmm.
That's hilarious. You didn't see the one drooling? Come on.
In liquids such as water, energy is low and the particles are tightly packed.
That's funny.
In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye, and they can be expanded and compressed in different pressures.
So pressure is a key word there. We're going to talk about ideal gases tomorrow, like I said, but gases have very big spaces between them. They have a lot of energy, so they can move away and kind of break those forces of attraction, keeping them close together. So the hotter gases are, what do you think? The more spread out or the closer they are? The hotter the gases get. If they gain more energy, because they're getting hot, they can move faster. Do you think that's easier for them to get away from each other or not? Not as easy? Yeah, easier, right? Yeah. So the hotter the gas, the more they can move and the more they spread out. So when gases get cold, guess what they do? Penguins. What do all the male penguins do in Antarctica while the females are out hunting?
They carry the egg.
Well, sort of. They kind of sit on it. They stand on it, sort of. You ever see anything on TV about that?
Happy
No?
feet.
They all kind of conglomerate? Anyways, they all get together and they huddle up for warmth. It's usually like negative 55 degrees out, so it's kind of cold. So yeah, they're huddling together because it's so cold and they're protecting the eggs. The analogy there is gas particles do the same thing. When gases get cold, they eventually, if you cool down the air in here, if we could cool it down enough, what would eventually start happening? Happens in the wintertime all the time. Snow, right. So the water vapor condenses to the point where it's solid. That's what snow is. So if you cool down a gas, the particles get closer and closer and closer, a liquid, then a solid eventually. So that's something you need to remember kind of throughout the whole year, that temperature, kinetic energy, how it's all related. What does temperature measure? Who has that definition? Go ahead and look. We wrote it down last week. What is temperature? Monica, go ahead. Measure of the average kinetic energy, right. So it's all this stuff is related that we're learning right now. So warm particles move quickly, they have high temperature, high kinetic energy, low temperature, moving slower. Gases expanding if they're hot, condensing if they're cold, right? So this theory actually explains a lot of things. So that's basically it for the video, I think.
All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
There you go. need water.
Davis.
Yeah, Corey Davis.
What?
Corey Davis.
Yep, Corey Davis.
Wow.
All right. Okay, lights, please.
It's a woman. That's not Corey Davis.
Okay, so I'm just gonna put kinetic molecular theory. Thanks. Okay, so here's the thing we got down so far. We have all particles are always in constant motion. Hot particles have high kinetic energy, moving fast. Slow moving particles have low kinetic energy, low temperature. They move randomly in straight lines. Right? That's everything we got from that. Yes.
Yeah.
Okay, we need to add some more. Okay, remember last week when I showed you the video, you don't have to draw this, of all the particles bouncing around in the box? Video, right? And I said, imagine that's the universe. Okay, we're going to go back to that analogy. So inside here is everything we know of. So mass and energy inside here, they're both. Mass and energy are always.
I have no idea.
Mass is moving.
Yeah.
Mass and energy. It's the two laws you looked up last week
Oh.
or the week before.
They can't. Yeah, I don't know.
Constant. Mass and energy is always constant. It's conserved. So mass cannot be created or destroyed, only
Transfer.
transferred. You with me, Riley? Energy cannot be created or destroyed, only
Transfer.
transferred. Good. So mass is transferred, energy is transferred. In here, it always stays constant. So in this little box, our universe, stay with me now. So in here, let's say there's 1 times 10 to the 1,000 joules of energy. Joule is a unit of energy. It's Joule, capital J is the unit. That's a lot of energy. So let's say that's the total energy in here. No matter what happens in here, energy, things can be lit on fire, things can be blown up, things can get cold, get hot, people eat things. All the stuff involving energy, overall inside this box, nothing changes. So, let me try and help you understand joules a little bit more first. Can I use my phone to look something up real fast? Thanks. I wrote this down 2 years ago, actually, so I could always come back to it.
It's ain't appropriate.
But it's for school. Isn't that what kids always say? That's not what
I've
kids say.
never heard anybody ever say that.
There we go. Okay, so a banana has 481 joules in it. So if you eat a banana, you'll get 481 joules of energy. So where's the energy coming from?
Banana. No.
Yes, but
Oh.
more specifically,
The banana.
Banana.
well,
It's a world.
you're thinking way too much. So I'm holding a banana.
Yes.
I don't need
That's
to.
a big.
Yeah. So I have a banana. I eat it, and I get energy from it. Where's that energy coming from inside the banana?
The banana.
Calories. The calories in the banana.
Yeah.
Well, potassium. You're thinking potassium. Okay, what holds everything
The
together?
particles.
Seeds.
The banana.
What class are you in? Chemistry. Okay, let's think in terms of chemistry. What's inside the banana?
Oh no.
It holds everything together. What holds us together? Bonds. Yes. Bonds. Forces of attraction. Yes. So, banana bonds. Yes. The bonds in the banana. So, there are bonds holding the banana together. Stay with me. Okay? When you eat the banana, you're breaking apart those bonds. You're using the energy. That's called chemical potential energy. Technically, I could eat this marker and get energy from it. Okay? Not much, because why? This isn't, our body can't do what to this?
Break it down.
You can't digest it, so you're not going to get much from it. Remember Arlena asked me about something about food and
Celery?
right? Wasn't it celery?
Yeah.
And I said if you eat only celery, you lose weight because your body takes
Well, you
more
said
energy.
something about how celery didn't have a lot of something.
Yeah. So
I don't know.
your body uses more energy breaking celery down than you get out of it. So if you were to just eat celery and that's it, you would lose all types of weight and you would probably get sick and have to go to the hospital. So it would not be good. That's not healthy. That's not healthy. So I'm just saying that was the analogy there, is that some things we eat actually require more energy from us. But a banana gives us energy. So that was 481 joules. I'm putting in perspective this number, this unit, joules. 2 tablespoons of peanut butter, 786 joules of energy. So 2 tablespoons of peanut butter actually has a lot more energy than an entire banana. Chicken breast, half a chicken breast, 1,000 joules. 8-ounce steak, guess. More or less than a chicken? More. 2,308 joules in an 8-ounce steak. So what I'm trying to get you to understand is when we eat food, we get energy from that food. I think you understand that. But it's in the bonds that we get it from. It's called potential energy. It's stored. We can turn that into kinetic. I ate a banana this morning. I'm using that energy right now. To breathe, talk, walk, move my hands. Everything we do, even when we sleep, we need energy. So we're using that. That's kinetic when we start using it. So it's important to understand what joule means. It's just a unit on a number. And what is that number? It's a number that somebody figured out a long time ago. A medium-sized banana has 481 joules. We could calculate it here. We'd have to burn the banana. We'd have to burn the banana and then capture, well, we'd have to capture all the energy it gives off using a thermometer, and it wouldn't be that hard actually, and we could come up with a number pretty close to 481. So you can measure this. I'm not trying to beat this to death, but I really I really like to have students understand things they're learning. So don't just memorize joules means energy and then not have any idea what joule means. So I'm trying to put it in perspective for you. 1 cup of spinach, 30 joules. Just throwing that out there. On a sweet potato, 477 joules. Sweet potatoes are so good. Who likes those? My daughter loves those things. She just throws it in there. Makes me nervous that she's going to choke. You can't. What? My daughter.
Just like a whole
she throws it in there.
Like a whole potato.
She sits in her little chair we have attached to the table, and when she's real hungry, we put like pasta. Forget it. She loses her mind. Pasta and sweet potato. She leans forward, doesn't even look at me, and just goes like this constantly. And she's little. We're like, don't choke, stop, slow down. So then I like have to block her hand. She's like, getting way off. Back to this. Now, what's conserved in here? What doesn't change? Mass and energy. Draw this picture, please. Okay, particle A, particle B are on a collision course. Particles are always colliding with each other, especially gases. We're going to focus mostly talking about gases, a lot easier to understand. So gas particles in this room, some moving fast, some moving slow. Temperature measures the average. Let's keep all this in mind. Let's say A has a kinetic energy of 100 joules. 100 joules. B has a kinetic energy of 50 joules. So they're on a collision course. They hit. A and B hit each other. And the particles are supposed to be the same size. If my drawing is not perfect, I apologize. So A and B collide. What do they do with their energy? Transfer. This was the boxing analogy I gave on Thursday, right? So Trevor and I were boxing. And he punches me in the face. Well, I feel it. Yeah, the joke was probably not. But yes, I would feel it. Because why? His arm, his hand has energy. Where's it going? Into my face. Okay? If you whatever, you walk out of here quickly, bell rings, you're like frantic to get to your next class or whatever, and you bump into the table and hit your hip, it's going to hurt. Okay? Yeah, I actually have a bruise right here, right now, because I hit one of those the other day pretty hard. So, anyways, it hurt because I am moving, and actually the table has energy too, even though it's just sitting there, it has energy. But when I hit it, that energy transfer, that's what I feel. So anyways, I think you get it. Things that collide transfer energy, right, Morgan? Good. So Morgan, these two hit, they transfer energy, write that down please. Transfer between A and B, they bounce off. They transfer energy, they bounce off. So now, remember, all of this is taking place in our universe, in the box. Two random particles hit each other, they collide, they transfer energy. All right, Morgan, give me the energy that each particle has after the collision. So before, A had 100 joules, B had 50.
Why do you always call on me for all the mathy stuff? I hate when you do this.
Maybe it's just like a subconscious thing that I know you're good at math, so.
No, I'm really not.
You will be in here.
No.
That's what I told Amber. She said the same thing. I'm like, forget the math out there. In here, you can be good at it. So you got 100 and you got 50. They come together. They transfer. Give me two numbers.
150.
Good. That is the total of the energy beforehand.
Okay.
So the total energy after also has to be 150. Very good. But how much energy does each particle have?
what it is.
But I don't know what it is, but it's whatever that.
Andrew,
They would have 50 and you have 100.
let's do what she says. Jake.
I don't know how to divide.
75 joules here and 75 joules here. Yes, but there's a reason I'm doing this with you besides teaching kinetic molecular theory. What's the definition of temperature? Measure of the average kinetic energy. Everyone here needs to memorize that because some of you I can tell already have. Some of you seem to not be interested when I'm going over that, or you're not listening. So make sure you know that, okay? Temperature measures the average kinetic energy. So Riley, what's the average between 100 and 50? If you were to add 100 plus 50 and divide by 2, it would be 75. So 75 is the average of 100 plus 50. So the entire system here, the universe, this is proving on a small scale, just one example, that the total energy before is always equal to the total energy afterwards. Why is that? Because energy is transferred, not created or destroyed. So it's conserved. So energy is never changed. It's always the same. It can just transfer. And then temperature comes in and takes the temperature of that. The temperature is always going to be the average of whatever scenario you're talking about. If it's 150, the average would be 75. The temperature, the thermometer would take the temperature of the 75. So if you could take a thermometer and stick it in this scenario, in this picture here, it would measure the temperature based on 75. Not the 100, not the 50, it would measure the average. So what are we trying to learn here? What are we getting out of this? The kinetic molecular theory says particles are always moving, random straight lines. Energy is always conserved. That's part of it. So when they hit, they transfer. But nobody loses energy or gains it, not really. If you start with 150, you end with 150. It's just where is that energy? This one lost a little bit, this one gained a little bit. But overall, it stayed the same. That's called an elastic collision. So why did I show you the rubber band? Yeah, this is elastic, basically. And the concept here is particle A and particle B. It's like the rubber band here without me stretching it out. When they hit and they collide, you're stretching it out. It appears to be changing, but then afterwards, it doesn't really change. It's still the same scenario as it was before. Yes, you can argue, yeah, but this one lost 25 and that gained 25. You're right. But overall, the whole universe, the whole scenario, nothing really changed. It's still 150. That was what I was hoping you could get out of this picture and this whole explanation. So that's called an elastic collision, and we're just going to write down what that means. I'm out of room. So elastic collision, particles transfer energy, but the overall energy stays the same. So particles, when they collide, transfer energy, but the overall energy stays the same. And that's called, technically it's called a perfectly elastic collision. That's what it's called, perfectly elastic collision. Okay, so the only other thing I got to add here, I got to make sure, let's see. So we have, they move in random straight lines. They transfer energy, but overall stays the same. The only thing we can add to this here, when particles collide, they change direction. That one's kind of an obvious one. If you throw a ball into a wall, it's going to bounce off going back a different way than it was originally going before I hit the wall. So particles collide, they change direction. That's it. That's it for the kinetic molecular theory. There's not a whole lot to it. The one thing I do want to mention that's not part of the theory, but something we defined today, chemical potential energy. That was the whole banana thing. Chemical potential energy. And that is what? Where's the energy come from in the banana? The banana bonds, right? Right, chemical potential energy. Energy stored in chemical bonds. We'll talk more about bonds down the road, and that'll make more sense to you. So potential means stored, isn't being used. You can take that, turn it into kinetic. That's what we're talking about with the movement and collisions. That's kinetic energy. All right. Questions for me? Chemical potential energy, energy stored in bonds. Okay, we got a couple minutes. Good. We can start talking a little bit about gases. You know your homework. Oh, I got those particle diagram quizzes. If you want to know what you got after class, you can come up if you want. I'll hand those back tomorrow when everybody's here. Any questions for me?
No.
Okay, we're not done yet. Not packing it up yet. All right. So this kinetic theory is a lot easier to talk about with just gases, so we're going to focus on gases now a little bit. So gases. What do we already know about gases? Adriana, give me something you know about gases. Like something to do with containers and volume and shape and all that.
No definite shape or volume.
Good job. No definite volume or shape. So what do they do then, Alexis? If they don't have a definite form and they don't have a definite volume, what do? So let's say I had gas in here. Secret gas. And then we... That was weird, I guess. Secret gas. We open it up. Secret gas goes into the room. What is the gas out of here trying to do? Or what is it doing as it leaves this container? What if this was filled with smoke? Good. Where'd it go? Would it go back there? Could it kind of go through the whole room and get all the way to the back and then hit the things and then the alarms go off? It could. Gases do the same thing. What's that called?
Diffusion?
Diffusion. Good. Give me another word.
That's fine.
That's all you got. That's fine. Someone else give me another word. Starts with a D. What? It disperses. Good. Through the room. Good. Give me a word. Starts with an E. I mean, that relates to gas or smoke. It's a good example. Coming out of here and filling the room. What does the gas have to do?
Evaporate.
It's already done that to gas. Expand, right. So,
Excalibur.
gases constantly, we'll finish tomorrow, constantly expand because they have weak
Why does
forces
that
of
water
attraction.
have so many dents in it? Like, it's just...